Welcome to our 3D printing and education presentation that highlights preparing Gen Z for the workforce in the virtual world we find ourselves in today. Hello, my name is Matt Griffin, Director of Community Development for Ultimaker. For the past 5 years, I have devoted significant time to supporting and collaborating with our education customers, especially within the Americas, because I strongly believe that this is a key area where 3D printing is making a lasting impact on our world already. My passion for this area bridges beyond even my role at Ultimaker to include activities such as co-founding the Construct 3D Education Conference in 2017. It is a pleasure today to share some of the recent resources I've been sharing with educators as they prepare for upcoming classroom, hybrid, and virtual scenarios. A little housekeeping before we get started. The presentation will last approximately 35 to 40 minutes. We will save time for your questions at the end, but feel free to ask your questions as they occur to you in the chat. Our aim is to highlight the role of desktop 3D printing within K-12 and university education contexts. We will bring you up to date with insights from Ultimaker's customers, including feedback from the field during the recent COVID-19 transformation. We hope you leave this presentation not only knowing what to look for in a 3D printer and better understanding of the scope and opportunities for 3D printing in education, but also with ideas you may immediately apply to better leverage 3D printing's strengths today. Here are the topics we will explore with you today. Review education stats, why 3D printing in education, where you encounter 3D printing technology in education contexts, inspiring project examples and how you can explore them also in a virtual or hybrid classroom, what you should look for in a 3D printer. So let's dive in. It is amazing how much 3D printing is growing worldwide each year, with 25% increase in North America and over 35% in South America in just 2019 alone. In fact, while it's difficult to project the numbers for 2020 and 2021 for obvious reasons, it looks like K-12 and universities are projected to be spending around $236 million in 3D printing by 2024. In comparison, companies in manufacturing, transportation, healthcare, and consumer goods will be spending well over $8 billion in additive manufacturing by 2024. Even though not every student will necessarily work with additive in the workforce, how does additive prepare our students with skills they need for their professional lives? Education has a long history with 3D printing stretching back to the 1990s, and some of the industrial machines were in fact developed at universities. There has been an explosion in adoption of additive manufacturing within the education sector since 2012, and this has a lot to do with the arrival of desktop 3D printers like Ultimaker's that now offer a range of materials, increased access, and lower costs of entry so that more educators, departments, and institutions can add this technology to their classroom and campus offerings. We feel that 3D printing is a perfect match for educators. 3D printing solutions themselves are a real-world example for a STEM career path, address learning outcomes specifically related to the expanding role of 3D printing in engineering, design, medicine, and manufacturing. As a tool, 3D printing can also produce visual, functional, and interactive teaching aids for other of the STEM and STEAM subject areas, address learning outcomes related to math, sciences, engineering, and technology beyond 3D printing. You aren't starting off alone. You can draw on a decade of classroom use, innovation from 3D printing education pioneers, address a variety of multidisciplinary learning opportunities beyond STEM and STEAM, boost engagement with tangible models and design in history, social sciences, English, and languages, facilitate collaboration and invention, and boost 21st century skills. While 3D printing in its first 2 decades largely focused on the role of rapid prototyping for parts that would be later manufactured using other materials and processes, the role of 3D printing today can extend from the earliest concept sketches all the way past validation prototypes. It is possible for truly functional mechanical prototypes to be produced and even final products. Each of these options are opening up the role of the technology for further iteration, testing, and even light production runs. Part of this expansion of scope is due to the larger range of materials that can now be used on the platform, including engineering-grade reinforced composites and property-specific materials, such as ESD-safe, medical-grade, chemically resistant materials. And part of this expansion is possible because the initial outlay, operational costs, and material costs, and the general all-around access to the technology is much more approachable when compared to previous models. This new class of technology opens up uses that were difficult or prohibitively expensive with older industrial use-restricted variants of the technology. While 3D printing's capabilities have increased, so have the number of departments and classes that now use this technology, expanding beyond the mechanical prototypes, architectural massing models, and design development prototypes to fully functional mechanisms, lush architectural context models, and product designs ready to share with potential stakeholders for feedback about ergonomics and key features. Consider this list of potential types of output from an FFF 3D printer. How can you map each of them to learning objectives for your course or lesson? 3D printing is a STEM and STEAM driver. Several studies over the past decade have determined that it is critical to expose students to STEM and STEAM mindsets as early in a learner's development as possible. A lifelong impact must be established within the first years of formal schooling, within K-6, especially for girls who might otherwise forego pursuing STEM careers at all. Grade school districts have found that introducing 3D printing to classroom activities strengthens interest and engagement in these areas, even in young children, 7, 8, 9 years old, who have demonstrated capabilities to design and fabricate their own creations, starting with software such as Autodesk Tinkercad. And at each new stage of schooling, there are other opportunities for students to draw on this technology to help them explore concepts and areas more deeply. Students who were first introduced to Tinkercad in grade school and have printed their first models are then able to scaffold on their past skills and apply 3D printing to new challenges. For example, printing plastic enclosures for an Arduino, Raspberry Pi, or Microbit for physical computing or computer science activities. As the students continue to explore these tools, they will gain the skills to 3D print mechatronics components for projects such as FIRST Robotics, where they can print using high-performance reinforced materials for linkages, mounting brackets, and other functional elements. In general, students who are exposed to this class of technology early continue to build on these first experiences to achieve more and more with 3D printing as they move into advanced and more focused study, leaving each stage of their academic development with a portfolio of what they have achieved to date. 3D printing teaches 21st century skills. More than anything, 3D printing is an opportunity for educators to help students to develop 21st century skills that will make a difference in all students' future careers, whether they pursue STEM, STEAM, or follow another route. Cross-functional research groups bridging from educational researchers, governmental task forces, and industry allies over the past 35 years have identified a new set of core competency skills that play a major role in the success of those entering the workforce to take up the new roles, requirements, and technologies that are critical to our competitive, skill-driven economy. Educators hard-pressed to identify class activities and challenges that clearly demonstrate progress in these 21st century skills have identified 3D printing as a boon to them, a way for students to apply knowledge to definable outcomes and persist, building resiliency as they master a novel set of skills. 3D printing has become the critical tool within the academic makerspace movement that aims to bring additive manufacturing and digital fabrication centers to educational institutions precisely because this mapping to 21st century skills can take place even within facility limitations and even with drastically restricted material options. In recent years, curriculum integrators, CTIs, along with instructors in history, social sciences, art, languages, and culture topic areas have discovered excellent ways to use 3D printing technology to help students engage with their historical and cultural heritage. Ideas ranging from student collaborative projects to propose monuments to overlooked community heroes and cultural traditions, to printing key one-to-one skull replicas from the prehistory of man. Popular online site repositories such as Umagine, My Mini Factory, Thingiverse, and Cults 3D offer a host of inspiring objects from archaeology, history, art history, society, and culture to get your classroom started. And these sites have been joined by public access 3D printable parts repositories at NASA, NIH, and the Smithsonian. One way this opportunity is addressed is with all campus access facilities. The Innovation Collab sites at Duke University offer over 100 Ultimaker 3D printers to a thriving academic ecosystem with over 20K potential students, faculty, and alumni operators, making the learning of 21st century skills accessible to a whole campus of students. So education is utilizing 3D printers, but what are they using them for based on grade level of the student? Now let's touch briefly on how this technology is used at each of the stages of a student's academic career. Starting with grade school, 3D printing helps educators illuminate otherwise abstract subjects, such as math, science, and history, with interactive experiences driven by printing. Introducing design early to students helps them take ownership of the lessons and subjects they are exploring and find personal relevance that may improve their willingness to pursue learning outcomes. Printed, unique designs also helps boost students' pride in what they can achieve and suggests routes they may want to pursue in the future in the direction of design, arts, engineering, and the sciences, putting on track to begin to develop foundational skills early in their educational careers. Skipping forward to late middle school and high school, the role of 3D printing in education changes. On one hand, it becomes more of a practical applied tool to produce parts, the context for producing parts of science experiments, for example. Popular examples include the evergreen egg drop physics engineering challenges, where students are challenged to develop a protective enclosure or vehicle to keep their egg from cracking. Also, unpowered, unmanned pine box derbies and nerdy derbies that add electronics and microcontrollers, where 3D printers can be leveraged to produce everything from a baseline vehicle to functional innovations such as steering and drivetrain to decorations and flair. In a similar vein, the same printing technology can also be a means to produce tangible mathematical visualizations to more easily explain algorithms and other abstract math concepts. But the technology can also play a key role in introducing iterative design development, human-centered design, and collaboration. Here, the ease of use and access to the technology helps introduce physical output that would require additional skills and training to produce using other fabrication methods. At the university level, the scope for the technology expands further. Printers are incorporated into the curriculum for everything from first-year courses to introduce digital practices to being a component of engineering capstone courses in the senior year. Students explore personal projects that help them develop the skills, understanding, and portfolio pieces that will prepare them for their future careers. Groups of students work together to solve design challenges and complete human-centered design prompts to invent products to serve hypothetical or actual members of the local community. And the value of these initial experiences with 3D printing extends beyond students' academic careers as they join the workforce and beyond. Especially in the wake of COVID-19 relief efforts, design and engineering firms are eager to hire junior staff who already have the basic 3D printing skills and experiences to help them amplify and accelerate their company's additive manufacturing strategy. Manufacturers are also eager to hire additive techs who can demonstrate via certification or portfolio projects that they have the training needed for roles in fabrication labs and services. So we've talked about the different roles for the use of 3D printing in grade school, universities, and beyond, but what are the contexts for where you will find 3D printers? At the school level, 3D printers tend to emerge in one of three scenarios. First, a homeroom or subject educator has mastered the technology and introduces it to students either as a means to expose them to design and digital design or to engage them more deeply in other subjects such as math or sciences. Second, a curriculum integrator supports an educator to include 3D printing in a lesson to expand scope of the lesson from a single subject topic to a multidisciplinary experience. For example, introducing design skills and iteration to a science experiment, creating visual demonstrations of abstract mathematics, or helping students touch history. This might involve 3D printers on mobile carts, checked out to the instructor, or time booked in a dedicated curriculum integration lab. As learning outcome requirements, budget, and school facility offerings shift, this area is under constant evolution and de-evolution. In a third context for K-12 educators, we have the academic makerspace. In several school districts and within well-funded or grant-funded schools, there is also the approach to offering an academic makerspace that allows educators to bring classes to learn about the technology and to use the technology for lessons. In some cases, an individual school may have a site, like the one shown here, and in others, a district will offer a single lab to serve several schools. In some cases, they are associated with subject focuses or after-school focuses, such as FIRST Robotics. In other cases, they are located within school libraries as a part of the movement to rethink libraries to engage in making and skill building as an aspect of serving their visitors. These labs have been gaining in popularity thanks to both the rise of the number of university academic makerspaces, the model for these types of labs, and the growing body of research pointing to the benefits of exposing students to these skills earlier and earlier. A number of funding routes, including local fundraising, have made it easier than ever before to add academic makerspaces to school districts. Initially, the place to find 3D printing in higher education was within departments such as sciences, engineering, architecture, mathematics, or visual art and sculpture. And the needs for the labs were tightly tracked to curriculum needs. With the emergence of the academic makerspace and general access labs, the teaching labs have expanded to include more than just capstones and final projects, but also for course use, introducing digital design and fabrication steps that students may in the future execute within general access labs, semester-long targeted research, engineering and design collaboration, and for the production of interactive models for abstract concepts such as fluid dynamics, higher math, physics, astronomy, cellular biology, molecular chemistry, and organic chemistry. The role has switched from the past, where the only access to 3D printing would be a single campus-wide printer, to the sequestering of machines to meet specific course needs for department majors. Speaking of academic makerspaces, the rise of these large-scale campus-facing facilities has been linked to everything from the aims of the dean's office to market facilities offerings to potential students, to offering core technology skills that may appear broadly in future roles and careers, to driving campus-wide cross-disciplinary collaboration between departments. In many cases, these facilities are used by students for coursework and personal projects, faculty for developing teaching aids and performing research, and for teams, for faculty, staff, and or students to collaborate to address community needs, invent solutions and products, and produce unique items for school spirit. In the early days of 3D printing within universities, operating the equipment was often considered an advanced skill requiring training. So a service within the university managed the industrial 3D printers on the behalf of the students, faculty, and staff requesting parts. These labs have evolved with the arrival of a larger range of affordable and materials-capable machines to offering advanced manufacturing capabilities up to and including 3D printing metal parts and medical-grade parts for the research. In some cases, students and student workers train in these facilities to operate advanced 3D printing equipment and master the range of materials and practices for leveraging professional desktop 3D printers like Ultimaker printers. These students can demonstrate to future employers at engineering firms, architecture firms, creative agencies, and manufacturers that they have advanced additive tech training and skills in these respective disciplines. Often outside of the school environment, but strongly augmenting teaching and learning resources where they are located, 3D printers within library makerspaces and museums bring the technology to a new set of problems and challenges. Libraries see 3D printing technology as an extension of their aim to provide knowledge and resources to those they serve, offering things like helping library patrons fabricate existing 3D patent models and other resources from model repositories. They also see the mission of making and design to be an important opportunity that they now offer. Community members create their own digital portfolios, invent products, and illustrate other learning experiences from their time at the library. Science, history, art, culture, and children's museums can offer everything from tangible models of precious or unavailable objects to encouraging attendees to engage in the scientific or cultural practices represented by a current exhibit by producing a new design or invention. With the arrival of the COVID-19 pandemic, schools were forced to immediately switch to online instruction, a challenge for serving hands-on experiences typically offered by 3D printing. Over the course of the spring semester, educators explored a wide variety of approaches to lessons in order to complete courses that typically involve the use of 3D printers. The story of how 3D printing labs helped with PPE production inspired many educators with real-world case studies to highlight in class. Project-based design competitions for 3D printed objects to help avoid the spread of COVID were also very popular. Many educators focused on 3D art, design software, and how technology like 3D printing fits within other digital design and fabrication technologies, a good way to use that aspect without the hands-on. Some academic makerspaces flipped to fulfilling parts or allowing students to use service bureaus to continue the printing experiences. Some educational institutions sent 3D printers home with students so that they might continue to use the equipment. And a key question many educators asked: how can you teach hands-on when students cannot have access to the equipment and printed parts? The value of this class of technology to educators hasn't vanished because of COVID-19, but the strategies for how to incorporate 3D printing has changed. Exploring this in a purely virtual classroom experience in 2020 has been challenging, but over the course of the emergency semester, already 3D printing educators found a number of opportunities to make this work well. We have collected a few inspirations that may prove useful to educators looking to continue to use 3D printing as either a key subject area or its ecosystem as a teaching tool. In the next few slides, we'll review digital practices, parametric and generative CAD design with the virtual world we are currently living in. While a printed part has frequently been used as a key outcome of a lesson, it is also a useful artifact and tool to illustrate a digital design process. And in courses without direct access to 3D printers, mastering the digital process to produce the pieces can itself be a key learning outcome. When you create something using a 3D printer, you create it 3 times. First, as a concept, where you must identify the need to use a 3D printer to produce the part, and select the route and machine, digital design tool, and material to use. Next, you create a virtual design created in CAD, 3D art software, or by tuning a generative system to produce a digital mesh model. This is a sequence that you can teach in your classes. Step 1, conceptual design. Identify the problem to solve, select a route for how to produce a final part, establish project parameters to guide design, software, hardware, materials, post-processing. And step 2, virtual design. Introduce 3D design software, use project parameters to produce the design, export a 3D mesh file ready for 3D printing. And finally, You prepare a 3D printing job where you translate the virtual design into a set of instructions that the 3D printer will follow to produce the precise final part, including material choice and slicing profile. What educators learned in spring of 2020 is that taking students through this process, even when they cannot print the output, still has serious values, especially thanks to access to Ultimaker's Cura preview mode, where it is even possible to click the animate button to see precisely the path order for how a specific layer might be printed. Mastering that entire sequence prepares a learner to understand design development and execution, and prepares them to understand fabrication processes that have multiple steps and dependencies, where decisions about machine, software, and materials play a major role in the result. And starting with this sequence before exploring each of these stages in isolation may help learners better navigate each of these 3 steps: shaping a concept into a design plan, designing a part in a virtual space, and preparing a print job with a set of raw materials. So, returning to our sequence, step 3A, physical fabrication. Import a 3D mesh file into Ultimaker Cura, select a machine, material, and printing profile suited to needs, evaluate the result using the preview mode. Were the right settings selected? And setting 3B, which is now, in this context, optional. Fabricate the parts. If the equipment is available, the instructor produces the parts. Use photos, video, and live video conferencing to share parts with students. Offer multiple routes to evaluate results. Iterate on this design. Here are 3 classroom context options for how to use this approach in your lessons. Virtual-only classroom. Introduce the entire 3-step design process and ask learners to make observations within Ultimaker Cura preview mode using the printing simulation tools. They can make observations about how specific design features will be executed. For example, how do you execute the top lip of an overhang, a shallow embed, or embossed detail, or a thin or thick wall? If the instructor can fabricate that feature and send photos and/or video reference back to the learner, that learner can then compare the results in terms of the intention, the physical fabrication, and the process simulation. Video conferencing allows the instructor to share webcam view of the part or Ultimaker Cura for a review of the simulation. An example would be designing letter stamps, and the teacher could try them out to see if they turned out the way the students designed them, helping them to redesign when needed. Hybrid classroom. The same lesson can be explored in a hybrid classroom by dividing the learners up into physical and virtual contexts. Offset students can focus on simulation in preview mode, while the on-site student can focus on observing the fabrication process. When both contexts share with each other, so that on-site learners can analyze how the machine produced the part differently from the simulation, and vice versa, this can fuel a conversation about the differences and similarities and what can be understood about future design processes as a result. An example, print a light stand where those who are in the class could test out the models and the virtual students create and provide feedback or iterative designing and fabrication. For specifically the asynchronous classroom, for instructors running an offset or flipped version of the lesson, the virtual and physical part analysis can be completed on a learner's own time, and then the act of sharing the off-site learner's expectations of the printed feature and the on-site learner expectations of the virtual simulation can be a moment to launch group discussions that highlight the differences between simulation and machine execution, so that learners can gain an understanding of what it means to plan for process technologies. For example, each student could design a puzzle piece and see if it fits into the others based on the parameters and iterate when needed. A great way to build upon your introduction of digital practices, design process, iteration, and review would be applying this process towards human-centered design, design thinking, and community projects. Let's review some examples. In this picture, club members at the College of the Desert provide feedback on how effective a set of 3D printed tactile models are for the blind and visually impaired. Participants identified what was and wasn't clear about each model to help iterate on designed parts. Which models are useful for teaching? Which models should be iterated, improved upon, and which models should be set aside? An idea in the classroom for these times would be to create a no-touch gadget to prevent the spread of COVID, like door openers and claws, to hands-free adapters for a sink. Rich Lair is a pioneer that was part of the Enable community. He got his students involved early on to create a prosthetic hand for his son Max, who was born with amniotic band syndrome. From hands, they moved to clips, and the prosthetic in the lower right is the latest version of Max's prosthetic, which is based on a high-res scan of a cast made of his residual limb and then modified in Tinkercad. Instead of designing what you anticipate an intended recipient would want, identifying a subject with a need and interviewing that subject to undertake both problem finding and problem solving can be an excellent resource for your students. And iterate attempts to meet the requirements for the solution for the subject to gain valuable insights about the effects of design and fabrication decisions on the resulting model. So, how do you choose a 3D printer with all that is available? Ultimaker has always strongly valued and supported education. Early innovators that were exposed to the technology as makers and students were the first champions for the desktop technology within a variety of industries, where these highly creative operators and expanding material options helped to reinvent an industrial technology that had stagnated after consolidation reduced competition to a very small set of primary vendors. The needs of educational institutions, educators, and students have always played a key role in what Ultimaker products we offer. As you are looking into what 3D printers to add to your school district or looking into 3D printing in your classroom for the first time, there are a few things to make sure to look into. What parameters should you use to select an appropriate printer? There are multiple technologies and all have different niche areas, but there are 3 parameters that the schools should always look at: the hardware itself, the software used to slice the CAD file and send the G-code for printing, and finally, the available materials, which is a primary driver of applications. Let's dive into these in more detail. Here are some hardware details to look into when selecting a 3D printer. How reliable is the printer? The build volume affects how big your part can be. How small can your smallest features be? Is the printer enclosed, and what is the maximum temperature of the bed and the head? Can you print continuously? If you run out of materials in the middle of the night, will the machine automatically switch materials? Is there a camera to monitor the print remotely? How complex is the setup? Can you unbox and start running in 20 minutes, or are you going to need a technician from the manufacturer and a special site to set up? Dual nozzle printing allows you to print with 2 materials. These are 2 model materials or a model material and a support, so printing in 2 colors is not an issue. Software has multiple components. The first is the slicer itself. Does it give you enough options to customize settings? Are there preset profiles to run any materials you want successfully? Are there profiles for different objectives like strength and dimensional accuracy? Here is the second piece of the software puzzle. Sending the print job from the slicer to the printer can be done manually with USB, but easier for the end user if it can be done via a LAN connection or via cloud, especially in this virtual world in education. Does the software have the ability to manage multiple printers and print jobs from a central location? Monitor, pause, resume, alter queue, reprint, firmware updates, track maintenance, etc. may be important to an academic makerspace. Materials is the third most important segment and probably what separates a lot of 3D printing companies. Many 3D printing companies have a closed system and their machines only run their materials. As you explore potential applications, look into open material platforms as well. The more materials you have access to, the more designs and applications you will be able to have for 3D printing. 3D printing has made great strides, and in the survey we conducted, we asked people their thoughts on the industry in general. We are glad to report that the sentiment towards Ultimaker is above the industry average, and these people rely on us to develop 3D printers for repeated use and reliable quality. Thank you for your time today. Let's go ahead and open up the floor for questions.
Hey, thanks, Matt. So I think I'm going to go ahead and jump out of this and we can jump over to your camera. I do have a couple questions for you that we got throughout the webinar. If you hold on one second, I'll go ahead and move that over to you. Once again, thanks for joining us and giving us a rundown on preparing Gen Z using 3D printing. So I'm going to go ahead and jump right into questions. So first I have, so what are some of the best project-based learning examples that you've seen so far?
Well, I mean, 3D printing has been a tool for project-based learning for pretty much, very popular since the desktop 3D printing revolution hit. So over the last 10 years, there's been just so many exciting projects. So there's always stuff you can go in mind, and some of the stuff people were bringing up in the chat gave some good ideas. What I found really interesting lately, from a particularly a virtual scenario like right now with everybody teaching from home, are ways that instructors have found ways to incorporate things around somebody's home or apartment, etc., in lessons and make things tangible, especially things. It's particularly helpful in teaching things like volume and some of the math related questions, but also just sort of breaking down functions of things. There are a lot of excellent examples that educators have been really generous to share, especially over the last since April, since sort of being stuck in the situation where everybody's kind of scrambling to change how they approach their plans. And so there have been a bunch of conferences and individual activities. I mean, this summer I helped to run the Construct 3D Summer Symposium, which was just educators sharing projects with educators. And so there's some great resources there, and and we'll continue to find and collect and share them that we can through Ultimaker. And Dynamism also has done a great job of mentioning them in some of their reach outs to folks.
Yeah, and I like how you brought up the things throughout the home. I think it was Mike that was mentioning that he was having the students design ornaments for their Christmas tree in the home. Yeah. So, and great example right there.
Exactly. Yeah, and kind of takes a little bit of the sting out of the, there's a constraint to what we can do right now, but you can use some of these options to take tools like 3D printing and make it practical, and then use that as a way to talk about how these kind of tools are being used for real world problem solving with things like like manufacturing aids and fulfillment centers and stuff. It's that some of these simple kind of things that you can make are actually not that different than what is being made by industry to speed up the processes to be able to solve a problem right there in front of them.
And you kind of mentioned the constraints, and I think that is a good segue into another question we have here. So with schools going virtual and students not having access to the lab, what are educators doing to kind of fulfill printed parts for students?
I mean, I mentioned a couple of the options, in the presentation, and Mike brought up in the chat, that he rescued some printers, took them home, and was able to, to print a bunch of stuff over a period of time, and then the next time physically meeting up with the students, got to play Santa. Is it good now?
Yeah. Can you hear me?
Great. Oh yeah. I lost you for a second there. It's sort of funny. I mean, that's one of the things that we're talking about here are people being resourceful and working around some of these complications. And so one of the things I wanted to share. So Mike showed he brought some printers home. I got a lot of calls from people in April who had raced home, but they were missing certain parts, and they wanted to keep their machines running because they were trying to find ways to keep the tangible aspect of 3D printing going. And here's this thing that I thought was quite interesting from the UNC team, because there is a makerspace there that had a hands-on curriculum program that they couldn't suddenly do. And so they had one challenge from a class that was already in progress when COVID sort of sent everybody home. And so they were forced to have the students do a couple more rounds of iteration virtually, and in playing in Cura and showing, making assessments on whether a 3D printed part would mesh with another real world object. And that team found that by having that extra virtual step before printing, that actually the results were even better. But then the staff printed those pieces and brought them, so they reduced the amount of printing they were doing to what they could manage, for that full class of participants. But there was a lot of back and forth leading up to the printing, and the final printing really represented, ended up being kind of a moment to demonstrate mastery of the topic, and it could be then they actually I think shipped them to the students after testing them on camera and showing which ones fit. So I thought that was really resourceful and a nice situation where it's exciting for the instructors who could take these home and could keep printing going on, even though they then had to do it. But you must be very careful about how much printing time you're committing to, because otherwise you can kind of drown yourself in part making, which is definitely a world that I've lived in by living with 3D printers for the last decade. But it's something that an educator needs to be mindful of, because printing is just an aspect of what they're doing.
Great. So I got a couple other questions here. So where are other educators that are doing virtual learning, where are they getting their lesson plans? Do you have any locations for us?
Well, actually one of the, I thought, Amber on the chat, who was mentioned it, she's in a library, but is also doing some curriculum development for local schools. We see a lot of situations like this where programs that are after school programs, or librarians who have really taken up the makerspace cause, have been very helpful resources for educators who haven't really been able to do this before and are trying to sort of do this for the first time in kind of a new scenario. So that's been really interesting to see, very helpful. There are a lot of projects online that you can see in the various repositories. They can be hit or miss, but there are a couple of repositories specifically for, or like lesson plan repositories, such as Create Education out of the UK. It's a really, really nice one, where you can go and see not only a lesson, and you probably aren't going to use it just as presented, but you can learn a little bit of the context of how the educators have used it. I helped create a list of some of these resources during that summer symposium for Construct 3D this summer. So it's a free list you can go get at construct3d.com. Construct 3D Conf, and you can go and see that list that links out to some of the stuff that the educators are posting.
One thing that I think we'll do
has resources listings as well.
One thing that I think we'll do is we'll follow up with some of these resources. For those of you still watching, if you have any other resources that you think other educators could benefit from, I think feel free to throw those in the chat and we'll distribute those. One that was already recommended was the City X project. And then I know another one that we have at Dynamism It is not a free option, unfortunately, but it's actually pretty affordable. It's like $100 or something like that. But PrintLab is a relatively new one that kind of walks you through the basics of 3D printing. It has ready-made lesson plans and stuff like that. And even some of the kind of walkthroughs have Tinkercad right there in the interface. And you're actually able to kind of play with concepts and 3D printing concepts like overhangs and infill and stuff like that. So that resources has been quite great. So, but we'll distribute some of
Yeah,
those
that's a
after.
good program.
One other question, I think this is the last one that I have, is I guess we already, so how are others using 3D printing in a virtual learning environment? I feel like we kind of crossed that, but did you have anything to add to that?
Well, what I started to suggest in brief in the presentation itself was using tools like like Cura in like simulation mode, in preview mode. What is also happening that is, I think, quite useful, there are more and more tools that are becoming either easier to access or cheaper to access for doing analysis on designs to understand things like, like basic loads and this kind of thing. That's getting a little bit more friendly for 3D printing and polymer 3D printing. And so these kind of tools are pretty interesting because they allow you to go further in assessing and at least bring up a conversation, like I mentioned in the presentation, about what you expect the part to be like before you print it, so you can get a lot more value out of the the virtual context, even without having that nice tangible win of printing it right in front of you. So I just wanted to reemphasize that. And when you take a look at this these projects again, when we send out the recording, etc., I suggest you take a look at some of those tools because they can be pretty handy. In particular, ways that you can go in there and quickly make pretty big changes between, like, say, layer height or number of shells, this kind of thing, and show them tangibly, and then potentially use an analysis package to show that you can get such a different performance out of these parts based on how you produce them, which is one of the key lessons, in general for how this technology is being applied in workforce, in industry itself.
If you guys have any questions, feel free to reach out to me personally or any of us. You can reach me at eric.b@dynamism.com. Or if you're looking for 3D printers in the classroom, feel free to drop by dynamism.com and look at what we have there.
Thank you very much for having us on here.